Welcome to the course on FPGA-based signal processing systems. We'll be doing the finite state machines. In the finite state machines, in the previous lecture, we had learned the Mealy machine and the Moore machine. So, what is the difference between that two different state machines? The input and the current state, which decides the output in the Mealy machine, and in the Moore machine, that is the current state purely decides the output. So here the previous example of Moore state machines and the Verilog module we had taken, and then seen that states moving with respect to the clock and the input uh, from one state to another, and what is the output, current state output in the Moore machine. So in the Mealy state machine, the example which you took, it's shown over here. The it has 4 states, and A, B, C, D. When the input is 0, the Mealy representation is the output is also 0. They stay in the same state. If enable is 1 or the input is 1, the output is 0 and moves to the next state, which is according to the state transition table we had considered. So this is the current state A, B, C, D, and when enable is 0, that it will move to the next. I mean, the same. The transition is only between it is staying in the same state, and the output is 0. And in enable is 1, move to B, and the output is 0. So from B, similarly, if the enable input is 0, then the output is also 0, and it is staying over the same state. Or if enable is 1, it moves to the next state, in which that the output is also 0. On C similarly, and the D and A, only when at D it gives output 1 if enable input is 1. So otherwise it stays in the same state. So the S asterisk S star is the next state, and comma the Z outputs we have represented in this table and the diagram as well. So now the state diagram, how do we make this in a Verilog module? The state machine module SM, that merely clock and enable. Clock is required to for the sequential circuit, like to move from one state to another, and with respect to the enable input. So enable and clock are 1 bit here, but outputs have been taken, the current state as well as the excitation excitation signal, or the output from the next state logic, that is called the next state, which is supposed to be passed to the current state and the next clock edge, because we use the D flip flop, and output is Z. So here is that the declaration of S reg and S next and output. So and then define states using the parameter declaration parameter, the 2 bits A, B, C and D, in which that A is 0, 0, 0, 1, 1, 0 and 1, 1. So A, B, C, D are 2 bits represented with the binary declaration. In one parameter declaration we have done this, similar to the case in the Moore machine, and only the difference, let's look at the next always, that is creating a state memory. That is the 3 important of always blocks. One is state memory, and the next state logic, and another one is the output logic, in which the state memory is created with always at the passage of the clock have this change this next S next to S reg, that is assign them using the non-blocking statement S next to S reg, and always at the at the rate of enable or S reg, the next state logic always block continues begin, and where the case check for the S reg choices. If it's A, then from the state table, if this is A and next state is A over here, else it is B. So these two are written over, that is using the if statement, if else statement. If it is B, next state is B, and this is C, next state else, next state is C. So similarly, if this case is C, next state would be C, and else next state is D. Okay, so D, if enable is 0, then D and A. So we have just considered this next states only in the always block, which is the default case is actually, you should put a colon, the default case is X next equal to A, and end case and end. Okay, so this is the always block which has the next state logic. Okay, so if we have the two always blocks, and one for state memory and the next state logic, and the next one which comes under the output, wherein we say the output logic, if you recall this Moore machine, which takes the SREG only as an input. Here the enable and SREG in the Mealy machine. So both are inputs to the output logic. So SREG enable is 0. So it goes to the next state as per the previous always block, and Z is 0. Also here this is else Z 0. We have this again. If enable is 0, then Z is 0, else also Z is 0 in two cases. Okay. So again the third condition comes into 0, fourth, if enable is 0, Z is 0, else Z equal to 1. So in all the cases, the enable outputs 0 and enable which decides the also output logic, here default and end case. So Z equal to 0. So this is the third always block which we had. And so the module, Verilog module, which consists of 3 always block, that is the style 1 separate always blocks for 3 blocks of state memory, next state logic and output logic has been shown over here. Let's see the output now. They're using the test bench. This code works. The module is state machine, merely test bench, and the inputs are reg, clock and enable. The output is sreg, snext and z, that wire. So these are 2 bits. So it is if it's good to observe both at the output, what is the current state and what would be the next state. So the next one is the instantiate in the test bench, the Verilog module what we had developed. So clock, enable, sreg and snext and c. So with the, after instantiation, this give the initialize those inputs, clock, enable, and then goes to the stimulus. So the stimulus we keep as we do display and monitor and $time, where clock, enable, sreg, snext and z are the signals we are going to observe. In this case, see the hash 50 which is giving enable 0, and another time enable is 1. After the 200 nanoseconds, enable made 0 and enable made 1. So how the states are moving for this case, this is end. So the stimulus is given in this fashion. So then we made the code for this, all generate the clock also, hash 50 clock equal to not clock. So with this test bench, the waveform editor show the clock. You'll have this clock edges, and then see the enable is 1, not at the clock edge, independent of it. So when there is a this sreg was 0 here, though the enable is 1 made over here, but it looks for the next clock edge to move to the next state. So this is next state, and then 1. This is 1 for next clock edge also, so it moves to the second state, and it is made 0 in between, so it stays in this state 2, that is 0 0 0 1 1 0. So here though because of 0, and then at next clock edge, before that enable is made 1, but it stays over here. Then at passage of the clock, that next test will be assigned to sreg. So this is moving to 3. And after that it is 1, so 0 0 1 2 3, and then 0 1 2 3 for every clock edge. It moves from one to another, because enable is 1, it moves in the A B C D. And the next is we can also observe next, which was supposed to be assigning getting over here. Okay, so the excitation signal, the excitation next state logic output is passed to the current state. You can see them over here, 3, and then over this is the case 2 is already there within this 0. So 3 and then 0, 1, 2, 3, 0, so on. Okay. So the same could be observed in the states S reg and S next and Z. This is output Z, and output we can see at this next state when it is it is moving to 1 1 state. It has to whenever it moves to 1 1, immediately because of the enable 1 and the output y equal to if you recall the output equation, that is enable into q naught star and q1 star, so that becomes 1 is that becomes 1, the output becomes 1 immediately till that next state of that a or a is 0 0. Okay, so this is the output which we get at the state D. Okay, so you can observe the same thing here into the D. So 1 1 and 0 0 0 1 1 0. It stays over here because of the enable 0 for some time, and then the enable is 1. All the cases that 0 0 moving from one state to another. 0 0 0 1 1 0 1 1 and then again to 0 0. So it moves over the other states. So the Mealy machines, that representation that we can get these waveforms from that. So we had taken the Moore state machine and Mealy state machine, which has only 4 states, and it depends on the enable input. The enable input which has an impact on the state, the output deciding the output. If enable is 0, then the output won't be enable is 0, depends on that the output will be here 0, but enable doesn't take any influence immediately and on the current state for the output in the Moore machine. So here in this case 4 states are same, Mealy and Moore, the example which we took, and some cases this the states may be more in Mealy or so for the given problem. So we'll take some of the Moore state machine, the examples, and get the state diagram and then develop the code for at least 1 or 2 examples. So for the Moore state machine here, the code or the diagram, which is this digital circuit which was using the D flip flop, 2 D flip flops 0 and 1, and which is connected with the combinational logic here and here also. If you closely observe, this gives the output logic. Okay, so which is taking q1 dash and q naught or so the equations obeyed by this is that z is equal to q naught and q1 dash. So this is output logic, and whereas the next state memory, if we take the state memory case, it is only the D flip flops of only these 2 flip flops will make a state memory in this circuit. So the 2 D flip flops makes the state memory, and this is the output logic. What about the next state logic? So it contains here. So we have this circuit which is giving the next state logic. So next state logic decides this D naught and D1. Okay, so what is this D naught here is it is getting the signal from Q naught dash as well as Q1. Okay, so Q naught dash and Q1, or that is D naught. This is D naught, and D1 is enable and Q1 dash. So enable and Q1 dash gives D1. So D1 is this. So in this we have the next state equations, that D naught and D1, and output equation C. So so from this the D flip-flop, what is the characteristic equation for this D flip-flop? Q0 star equal to D0 and Q1 star is D1. So writing this Q0 star equal to Q0 dash Q1 transition equation, and then obtaining Q1 star equal to D1 here. So substituting them over here, we get this Q0 star and Q1 star and make the state transition table here. So the state transition table is obtained. So Q0 and Q1, there are two flip-flops outputs. So two states 0 0 0 1 1 0 1 1. So the combinations could be of 4 states. This particular digital circuit will have these 4 states. So the enable input, if this is 0, from the equation that Q0 star and Q1 star, what we had got over here, that is Q0 dash plus Q1 and enable Q1 dash. Okay, so using this equations, we get 1 0 as the next state. If this is if these two are 0 0 and enable is 1, this becomes 1 1 and 1 0, and here it stays over here 0 0 0 1 1 0 1 0. So from this we assign this alphabets to the states just to identify here. So this is considered to be state A, and state B, state C, and state D. So if we have this ABCD, so then we can also replace this next states with ABCD. So here the state names here 1 0 is C, again 1 0 is C, 0 0 is A, 1 0, just map it DD, and this is C and B and 1 C. And what is the output using the output equation? So finding out for this 0 0, what is the output? So the current state, what's the output? When it is 0 0, the output is 1 or 0 1 1 1. So this is S star, then the next state, and this is the output for the state machine. So obtaining the state transition table from the digital circuit, and we now ready to make the Verilog module for the state machine. So the equations given here, using these equations we have made this. So Z is Q0 plus Q1 star. This Q0 and Q1 star is from this 0 0 0 1 1 0 1 1. So after getting the state transition table, we go to the use this. Also we can have the state diagram. If this is from the, so if there are A, B, C, D, B, C and D, there are 4 states, and if enable is 0, A is going to that is C here, this one is C, and next state, if enable is 1, it goes to D here, this is the one next state. So B, from B it checks for enable 0, go to C, and enable 1 also go to C. So whatever the info, the enable you get, go to C here. The next state is C and C, and C at C, the enable 0 points to A and enable 1 points to B. This is points to B here and 0. Also at D, enable 0 go to C and enable 1 also go to C. Okay, so there are this is the state diagram of this the digital circuit. What we have systematically we obtain this step by step, we obtain the state diagram. So the first identify this excitation equations, and then get the characteristic equations, state transition equations, and then the output equations. After that, make this table and get this diagram. Now with this data, that what we have is sufficient to have develop the Verilog module. So now let's take the module. So state machine 1, the clock and enable, the output Z, output also we have taken SREG and SNext in this. So the registers which is declared as this Z is SREG and SNext are used in the always block. The declaration of net declaration is done, and then parameter declaration which is defining the 4 states 0 0 0 1 1 0 1 1 ABCD. These are 2 bits. After the declaration, take the state memory. the state memory always at passage of the clock take the S reg is getting the S next. Okay, so here the always at passage of the clock the S next is assigned to S reg and with a non-blocking assignment. This is the state memory, and the next always use this table for writing the next state logic. Always at the rate what is the next state logic inputs are enable and S reg, that is the next state logic. So begin case S reg. If enable is 0, that is for the state A, move to state C. Okay, this is only giving the next state. Else enable is 1, that means no to next D, next state D. If at B, similarly enable is 0, go to C, and it is again C here. Else also C. If at the current state C, again the next state A, next state B. That is this is the code. Else if enable is C, enable is 0 at D, this goes to C, or also it goes to C. That is default. And then yes, next you can have as a 0 0. Okay, end case, case and end case. After that end. Okay, so this is the next state logic fully the always block which contains the details of the state transition table, and then come to the output logic, which is the output for next always block. Always at the rate S reg. If current state is this, give the output as in the output logic. The word case reg in the cases 1 are A, C and D. So the choices of A, C and D can give for Z equal to 1. Other case only B, at the current state B it is 0. So this is the case, default and end case, end module. So this is the output logic we have from the state diagram. So once we have the digital circuit and getting this state transition table with along with the output, so the code can be 3 always block, 1 for the state memory and another one for the next state logic transition, and the output also can be written this way. Next, the test bench, I would give that state machine test bench, which gives the input clock enable and the outputs what we defined already. Instantiate the module, which is the SM1 test bench, and then initialize the inputs clock enable and then stimulus. So the stimulus can be having the display and the monitor signals. Also this is the portion which is very important, how you try to move the state machine, what is to study. That enable 0 1 0 1, that is just changed to test whether this with respect to the enable it keeps moving to the next state or not. Do not forget to generate the always always a hash 50 clock equal to not clock. This is 100 nanoseconds clock. It can be of your choice. And then the given the table, what is the viewform editor, the table what we had got it. So the clock edge can be marked, and then the passage of the clock we are using. So the enable 1, the enable 1 at this point, it is because the enable is 0 initially, it is at the 0, and when enable is made 1, here this is 0, this is at 0, and enable is 1, it is going to D, that is here. Okay, at D again enable is 1. Okay, so here it is going to C. Okay, here going to C. So at this point C, and then enable is made is 0 here. Okay, so it is going to 0 0, that is state A, and then to move enable is 0 here at a 0, enable is 0, it goes to C. From C again enable is 0, it is going to A. Okay, so easy this movement 0 2 0 2 you can see, and then move to enable is made 1, so it moves to from 0, this is going to D here. Okay, so from that D enable is 1 again here, so it moves to C. okay, so T, and then so on. So the next state also could be observed, how this is getting transferred with respect to the clock, okay. So the console also gives the outputs, how the state SREG is moving with respect to the enable, also the S next movement. So Z is 1 in these cases, because 1, 3 and 3 it is moving between only here the SREG, the output is 0, that is over 1, that is 1 and it is 0. The output is 0 in this clock pulse, clock total duration of the time clock. So the for the given the circuit, again the state machines, the module which is moving from one state to another could be observed from this waveform editor. The design what we had done from the digital circuit to the state diagram is works in the way it is expected. The module, the Verilog module, which we have developed, is the with 3 always block, okay, style 1 of the behavioral model. So now the taking another example, which is just to have so far we have considered this 2 bits in the states, okay. So there were 2 flip-flops and one more extra flip-flop. This is the 3 flip-flops, this example. Anyway, the 3 flip-flops, so we have this will be 8 states in that. So Q0, Q1, Q2, Q3 outputs forms a state value 0, 0, 0, 0, 0, 1 and 8 combinations you would get, and the equations corresponding to them can be obtained. Here is the D2, if you see, where it gets this Q1 XOR Q0, it is Q0 and this is Q1 XOR this function, and then XOR of the other one, that is here Q1 and here is Q2 or them and NOR. So you get this as a Q1 dash and Q2 dash. So this one, and both are given to an XOR gate. So XOR is this. So which gets the output gets into D2, and then D1 will be equal to Q2. D1 equal to Q2, and Q0 star is D0, and then Q1 star is D1, Q2 star is D2. Okay, so we get this. So D2 expression, we just certainly would like to have this. D2 is this bit. Okay, so which gives here D2. Okay, and D1 is Q2, fine, and here we have this is D0, which just change the order, D0 equal to Q1. Okay. So of course Q0 star is the D0 and that is fine, and Q1 star is D1 and Q2 star is D2. This is okay. So here only the expression of D2 gets D2 we get is from here. Okay. So the logical expression what we have. So this equation, kindly note the change in this D2, and D0 is going to be Q1 and D1 is, it's all right. Okay, so the exchange of the symbols D2 and D0. So in this example now with this the order in which the D flip-flop is drawn is the one. So the next state logic, which is giving this output, which gets into the D2. So this is going to be the next state logic. Okay. Whereas the flip-flops make the flip-flops make the state memory, and if there is any output logic here, there is no combinational circuit for the output logic. So it's simply Q0, Q1 and Q2 are the outputs, that those are the current states. So the current states are going to give the outputs. Q0, Q1, Q2 are the three of them will give the outputs here. Okay. So you can see the synchronous clock which is going to all the flip-flops, that is fine. Next is logic and the state memory, and the output logic only Q0, Q1 and Q2. So from this we can have this Q0, Q1 and Q2, which is calculated that okay, this is the state. We have three bits, so A, B, 8 combinations of it, and Q0 star, Q1 star, and Q2 star, which is calculated over here using this D0, D1 and D2. Of course, this is D0 equal to Q1 and D2 is this D1 equal to Q2. So using this, what we have obtained is that when it is 0 0 0, Q0, Q1, Q2 dash becomes 1 0 0, 0 0 0, 1 0 1, and so on. So the using the equations what we had here, that we got this the states. Okay, so and next is assign this A B C D E F G H over it. So from A to H. Okay, so there are 8 states over here, and this is E. Of course, this state is E. So next is E, next is A, and this is F. So assigning this states A B C D E F G H and E A the corresponding D and so on. So the how this is moving without any enable input also. So it doesn't have this enable input. This states will move with respect to the clock. So from clock, first clock edge it is A at A, and then next clock edge it goes the passage of the clock, that is it goes to E or neg edge also. It can be changed A to E. So A to E, and from E if you see that goes to C. And then from C it should go to F, and then from F F it goes to G, and from G it is going to H, and H it is going to D, and from D it is going to B here, and from B this goes to A. So it completes that this fashion the next state with respect to the clock. So this is the state diagram we had obtained. So for this, if we take there is no input here, so you can mention only the input as a clock, only the clock, S reg and S next. So S reg is next, and the bits, the parameter, we can have the 0 0 0 0 1 0 1. So 3 bits are defined, so which is having all the 8 states defined using the parameter. Next, the state memory S next is assigned to S reg. So again the state table I have just put it for the reference here. So we have this next state logic. How do we assign this? If in the case always at the passage of the clock, and S reg, which is going to be the next state logic in the, deciding the next state logic. So that if in A next state is E, simply there is no other condition here, if else conditions, because no input enable is used in this example. So simply S next is A, and if it is B, S next is A here. If at C, S next is F. So and so on. Continue with this H equal to H at H, S next is T. Okay, so if S reg is going to be the A, B, C, D, these are the cases, and then default S next is A. End case. So next state logic doesn't have the input here. Okay, that this is only the passage of the clock, it keeps moving. Okay, so this can be very well used as a counter design. If you decide the counter example, suppose it is going to be a 3-bit counter from 0 0 to 1 1 counting. So just define these states as A B C D E F G H, and then move it over the clock edge. So the module test bench, we have this, instantiate them, and then we just want to give the initialize the inputs, then wait for this global reset, then stimulus would have you can notice that there is no change in the no specification of input, enable input or something. Only we need the clock which needs to move the state machine states from one to another. So here is the output. We get the clock, every clock edge. Yes, it is every clock edge. We have this S reg for the first 100 nanoseconds, and then we have this is up to here. Okay, S next is assigned to S reg. So S reg at the next passage of the clock 0 0, and then the 4 1 0, and then this is 1 0 0 0, the next state, that A B C D that state. 4 next to 2, 5, you can have this here as well, A, and then E, it moves to E here, which is, and then C is 2 given. The radix is mentioned in decimal, so you have this 2, 5 F, 6 G, and then 7 is H, and then here 3, okay, again 1, and then 0, it comes back here. So for if the with respect to the clock edge, it moves from one to another. The next was the previous, it is the output of the next state logic, which has the combinational circuit in that, deciding the input to the flip flop. So the same could be, this SREG is over here. You can observe that it is moving from 0, 4 to 5, and then 6, 7, and then move into 0. So this completes the Moore state machine. So at the current state, with even without any input, the counter, this is a typical example of a counter which can be used as a as a state machine, which we can develop the counter module also, the 3-bit counter or the 2-bit counter as a state machine in this fashion. So decide the present state, next state, and with respect to the clock edge, you can move it, or the state table can be made with the input. If enable input is 1, move from 1 to here, or if it is 0, stay over there. So that fashion can also be designed with this type of example. So this is equivalent to the counter example, and then the other example which we had is, doesn't have this output logic, but we have the state itself is a output logic. In this case, both enable input and output is not there. So these examples clarifies the Moore state machine and the module for developing the Moore state machine with 3 different always block in style 1 fashion, and we'll be doing that different styles in the coming week. Also we'll be doing the few more state machine examples for the Mealy machine and Moore machine in the next lecture. Thank you.